In the vast, arid landscapes of Namibia, where water sources are scarce and distances stretch beyond the horizon, African elephants have developed an extraordinary ability that has remained hidden from human understanding until recently. Join us as we explore the groundbreaking research that has uncovered a sensory world existing beneath our feet, where elephants can perceive, interpret, and respond to seismic vibrations traveling through the ground across distances exceeding 20 kilometers. This remarkable discovery transforms our understanding of elephant cognition and opens new windows into evolutionary adaptations that could change how we approach conservation and technology. Between 2019 and 2021, the ElephantVoices project, led by Dr. Caitlin O'Connell-Rodwell, conducted groundbreaking research in Namibia that revealed something extraordinary about African elephants. While scientists had long known about elephants' use of low-frequency vocalizations that travel through air, this research uncovered a parallel communication system operating through the earth itself. The elephants were essentially using the ground as a communication medium, detecting vibrations that humans cannot perceive without specialized equipment. This discovery represents one of nature's most sophisticated sensory adaptations and dramatically changes our understanding of how these intelligent creatures navigate and communicate across vast distances. As Dr. O'Connell-Rodwell explains, what we're observing is essentially a sixth sense. Elephants are reading the landscape through their feet, creating mental maps based on vibrational signatures that humans can't perceive without specialized equipment. At the foundation of elephants' seismic perception are specialized mechanoreceptors called Pacinian corpuscles. These structures, which resemble onion-like layers of tissue, are densely concentrated in elephant feet and trunk tips. Exquisitely sensitive to mechanical pressure and vibration, these receptors rapidly convert the mechanical energy of seismic waves into neural signals. These signals travel via dedicated neural pathways to a specialized region in the elephant brain that neuroscientists now identify as the Seismic Processing Center. Comparative brain imaging studies conducted in 2020 revealed that this region functions similarly to the human auditory cortex but has specifically evolved to process vibrational data rather than airborne sound waves. The sensitivity of this system is truly remarkable. Laboratory tests conducted at the Namibian field station demonstrated that elephants can detect seismic signals with displacements of less than 1 nanometer, approximately the width of a hydrogen atom. This extraordinary sensitivity allows them to distinguish between subtle variations in seismic signatures, effectively reading the landscape through tremors and vibrations that permeate the Earth's crust. When actively listening to the ground, elephants adopt a distinctive posture that enhances their seismic perception. Researchers have documented elephants freezing in place, shifting their weight forward, and sometimes lifting one foot, a behavior that reduces self-generated noise and optimizes the reception of incoming seismic signals. This posture, nicknamed the seismic stance, has been observed consistently across African elephant populations, suggesting it represents an innate behavioral adaptation rather than a learned response. The stance allows elephants to minimize their own interference with the subtle signals they're trying to detect, much like how humans might cup their ears or turn their heads to better hear a distant sound. This behavior is particularly notable because it demonstrates conscious manipulation of their body position to enhance sensory input, a sophisticated cognitive process that further highlights elephant intelligence. The practical applications of this seismic sense extend far beyond basic communication. Elephants have demonstrated an ability to categorize and respond to at least 4 distinct types of seismic information, creating a multi-layered understanding of their environment. The first category involves natural geological events. Field observations have documented herds changing direction to move toward distant water sources that have recently filled after rainfall events more than 15 kilometers away. The elephants detect the subtle seismic signatures created by water percolating through underground aquifers, signals imperceptible to human senses. Even more remarkably, multiple instances have been recorded of elephant herds moving to higher ground hours before earthquakes occur, responding to the preliminary seismic activity that precedes major tectonic events. This ability to detect geological changes from vast distances gives elephants a significant survival advantage in arid environments where water is scarce and unpredictable. The second category of seismic information that elephants process involves anthropogenic vibrations, those created by human activity. Elephants recognize and systematically avoid vibration patterns associated with vehicles, mining operations, and human settlements. GPS tracking data from collared elephants in the Kavango-Zambezi Transfrontier Conservation Area shows that herds alter their migration routes based on seismic disturbances from new mining operations, often before visual or auditory contact would be possible. This sensitivity to human-generated seismic pollution raises essential questions about how infrastructure development may disrupt elephant movement corridors through mechanisms previously unconsidered in environmental impact assessments. Roads, railways, and industrial activities may be creating invisible barriers that fragment elephant habitats not through physical obstacles, but through seismic disturbances that elephants perceive as threatening or disorienting. Biological signals constitute the third category of seismic information that elephants process. They can identify the movement patterns of predators like lions through subtle ground disturbances, allowing herds to avoid danger. Matriarchs have been observed initiating defensive formations after adopting the seismic stance, despite no visual or olfactory indication of predator presence. Subsequent investigation frequently revealed lions or other predators approaching from downwind, detected solely through their seismic footprint. This ability gives elephants a crucial advantage in predator-prey dynamics, especially in protecting vulnerable calves. The matriarch's experience in recognizing these subtle seismic signatures highlights the importance of elder elephants in herd survival, as they maintain a mental library of vibrational patterns associated with various threats and can distinguish between dangerous and benign disturbances in the environment. Perhaps most sophisticated is the fourth category of seismic information: conspecific communication. Elephants deliberately generate their own seismic signals through specialized behaviors. These include coordinated foot stomping, head pressing against the ground, and the production of specific low-frequency rumbles that couple with the terrain. These self-generated signals follow syntactical patterns that vary based on the message. Alarm signals feature rapid, high-intensity vibrations, while directional information is communicated through rhythmic sequences that appear to encode spatial data. Family groups maintain contact across vast distances through regular, check-in vibrations that announce location and status without requiring visual contact. This sophisticated communication system allows elephants to coordinate movements, warn of dangers, and maintain social bonds across distances that would otherwise make group cohesion impossible in their expansive habitats. The implications of these discoveries extend far beyond elephant behavior, connecting to unexpected fields and inspiring technological innovations. Architectural engineers at the Technical University of Munich have begun studying elephant seismic sensitivity to develop more sensitive vibration detection systems for earthquake early warning networks. The elephant's natural algorithms for filtering signal from noise outperform many current artificial systems, particularly in distinguishing relevant seismic events from background vibrations. Dr. Marguerite Jen, lead engineer on the Munich project, notes, "The elephant brain solves problems our most advanced sensors struggle with, specifically, how to extract meaningful signals from a noisy environment. We're now developing biomimetic seismic sensors based on the structural properties of Pacinian corpuscles, and early tests show a 40% improvement in detection thresholds compared to conventional sensors." This cross-disciplinary application demonstrates how understanding animal adaptations can lead to significant technological breakthroughs that benefit human society. Meanwhile, paleontologists at the University of Bristol have used this research to reinterpret sauropod dinosaur anatomy. New analyses of fossil evidence suggest that these massive creatures may have utilized similar seismic communication networks across the Mesozoic landscapes. The distinctive columnar legs and unique foot structures of sauropods bear remarkable similarities to modern elephants' seismic-optimized anatomy. This perspective potentially explains previously mysterious aspects of sauropod social structures and migration patterns, suggesting that seismic communication may have been a crucial adaptation for megafauna throughout evolutionary history. This connection between modern elephants and ancient dinosaurs highlights how certain evolutionary solutions may recur when animals face similar environmental challenges, despite being separated by millions of years. The discovery opens new avenues for understanding prehistoric ecosystems and the communication methods that may have facilitated the success of the largest land animals ever to walk the earth. The practical applications for elephant conservation have been immediate and significant. The Elephant Listening Project has successfully developed seismic fences, devices that generate specific ground vibration patterns interpreted by elephants as warnings, to prevent human-elephant conflict without requiring physical barriers that fragment habitats. "We're essentially speaking to elephants in their own vibrational language," explains Dr. Lucy King, who implemented the system in Kenya's Amboseli region. The reduction in crop raiding incidents has been dramatic, over 87% in our pilot areas. Unlike physical barriers or traditional deterrents, these systems don't prevent natural migration patterns or access to critical resources. This innovative approach represents a breakthrough in conservation, allowing humans and elephants to coexist more peacefully by communicating across species boundaries using vibration rather than physical barriers. The technology respects elephant intelligence and natural behavior while protecting human livelihoods, creating a more sustainable solution to a persistent conservation challenge. The research continues to expand, with new studies investigating how climate change-induced soil composition alterations may affect elephant seismic communication networks across Africa. Preliminary data suggest that increasing soil desiccation in certain regions is degrading seismic signal propagation, potentially disrupting age-old migration routes and contributing to observed changes in elephant behavior. As climate patterns shift and landscapes transform, the very medium through which elephants communicate, the Earth itself, is changing in ways that may interfere with their ability to find water, avoid threats, and maintain social connections. This represents yet another subtle but potentially devastating impact of climate change on wildlife, affecting biological processes that we've only recently begun to understand. The disruption of seismic communication networks could have cascading effects on elephant populations already facing numerous threats, highlighting the complex and often invisible ways that climate change impacts ecosystem functioning. This discovery of elephants' seismic sensory capabilities fundamentally transforms our understanding of these remarkable animals and challenges our anthropocentric view of sensory perception. While humans have evolved to dominate visual and auditory processing, elephants reveal entirely different evolutionary pathways that harness the Earth's constant whispers. This research also highlights how much remains unknown about the sensory worlds of other species. Recent studies suggest that giraffes, rhinos, and even certain rodents may possess similar abilities, though less developed than elephants. As technology advances, we may discover that the ground beneath our feet has always been alive with communication, conversations happening in frequencies and forms that our limited human senses have been unable to perceive. This expanding field of research invites us to reconsider how we understand animal intelligence and sensory experience, moving beyond human-centered metrics to appreciate the diverse and sophisticated ways that other species perceive and interact with their environments. As we face unprecedented environmental challenges, the elephant's seismic sense offers inspiration for technological innovation and urgency for conservation. By learning to listen to the Earth like elephants, we may develop new approaches to environmental monitoring, disaster prediction, and wildlife protection. The biomimetic sensors being developed based on elephant physiology represent just the beginning of potential applications. Future technologies might include distributed seismic monitoring networks for early earthquake detection, underground water mapping systems for drought-prone regions, or non-invasive geological survey methods that reduce environmental impact. The elephant's ability to filter meaningful signals from background noise could inspire new algorithms for data processing in various fields. These innovations demonstrate how understanding and respecting the sensory worlds of other species can lead to technological breakthroughs that benefit both humans and wildlife, creating a more sustainable relationship between technology and nature. The discovery of elephants' seismic communication system represents one of the most profound insights into animal cognition and sensory perception in recent decades. Through specialized mechanoreceptors in their feet and trunks, these magnificent creatures can detect vibrations smaller than a nanometer, allowing them to monitor geological events, avoid human disturbances, detect predators, and maintain complex social networks across vast distances. This ability has evolved over millions of years, creating a sophisticated sensory system that operates in ways fundamentally different from human perception. As we continue to study this phenomenon, the applications extend from conservation to technology, inspiring more effective earthquake detection systems, reinterpreting dinosaur behavior, and creating innovative solutions for human-elephant conflict. Perhaps most importantly, this discovery reminds us that intelligence and perception take many forms, and that wisdom sometimes lies in recognizing the limitations of our own sensory experience of the world. By learning to listen to the Earth as elephants do, we may not only develop new technologies and conservation approaches, but also gain a deeper appreciation for the complex and beautiful ways that life has evolved to thrive on our planet. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.